So basically what I'm going to talk to you about today is NICER. NICER is the Neutron Star Interior Composition Explorer. And it's this kind of little box, if you can see kind of up here behind me on my space station backdrop, sits on the International Space Station. And its goal is to take observations and use those observations to try and understand what is lurking inside the neutron star interior. Now, in fact, it ends up doing an awful lot more than that. It does black holes and all kinds of other fun X-ray observations as well. But my focus of the work that I'm doing at the moment is really on the neutron star side of things. And of course, being a NASA mission, it has a beautiful mission patch as well, which I'm also going to come back to later in the talk. So I should start off by explaining, why anyone would possibly care about the neutron star interior. And this is because they're really intriguing objects. I mean, these are the collapsed remnants of, massive stars, not massive enough to make a black hole, but progenitors somewhere perhaps in the range 7 to 15 solar masses or so, collapsing down to maybe 1 to 3 solar masses of material in an object, with kind of 20 to 30 kilometers perhaps in diameter. So extremely, extremely small, dense objects. We know thousands of neutron stars basically in the galaxy. The vast majority of them are radio pulsars. A large number are also X-ray pulsars, and that's what I'm going to talk about today. Some of them are on their own, some of them are in binaries, maybe just orbiting other stars, and others are accreting material from companions. They're perhaps with white dwarfs or normal stars. So they're in all kinds of intriguing systems as well. In terms of our theoretical picture of what a neutron star is, not just neutrons, basically, is the very, very short answer. We think they have a complicated layered structure. So actually, they're a little bit more like a kind of mini planet in some respects than a regular star. Outermost layers, we think we have a solid crust of some kind, perhaps 1 to 2 kilometers thickness, which is an ionic lattice. And the ions themselves change composition as you go deeper and deeper into the star, with the nuclei gradually becoming more and more neutron rich. In the outer crust, the dominant pressure component comes from degenerate electrons, so it's kind of white dwarf material. As you come down towards the inner crust and the nuclei are getting more and more neutron rich as you're crushing matter together, eventually neutrons are going to start to drip out of the nuclei as well, because that's then the stable state. So in the inner crust, I have kind of, a nice ionic lattice, I have degenerate electrons, and now I also have some free neutrons floating around as well, and most likely those are in a superfluid state. And that leads to all kinds of entertaining dynamics and things as well. Once we get down towards kind of nuclear densities at the base of the crust, essentially the whole thing becomes most likely some kind of ultra-dense nuclear fluid. Densities may get up to several times that of a regular nucleus. And we really don't know exactly what the nature of the matter is under those conditions. Chances are it is extremely neutron rich. And by that, I mean something like perhaps 90%, maybe 95% neutrons, perhaps at least in the outer core. So an extremely ultra dense nuclear fluid. Still have to have some protons floating in around there and electrons for balance. But there are lots of other potential things that could be forming as well. Because the gravitational confinement within a neutron star buys you time for things like weak interactions to operate as well. And that potentially allows you to form stable states of strange matter in the cores too. Now, those strange quarks, up, down, and strange, could be locked up in particles like hyperons, 3-quark particles. They could be in the form of condensates, or they could be even in the form of deconfined quarks. And our particle physics colleagues are incredibly creative at coming up with all kinds of fun things that could well be lurking inside the cores of neutron stars. So that's the bit that we really don't understand terribly well. And just to put this kind of in a wider context, we're not the only people trying to understand, the nature of the extremes of matter. So what I'm showing basically on this slide here is, my deeply simplified phase diagram of the whole universe. On the y-axis, we've got temperature. And on the x-axis, chemical potential, roughly density, depending on whether you're a nuclear physicist or an astronomer, going along the x-axis. We live down in this kind of bottom area, basically yellow down here, and all the matter around us, is in the form of hadrons and nuclei. What we want to understand is what happens as we go to extremes of temperature and extremes of density. And unfortunately, it's really hard to calculate that from first principles. We have this beautiful theory, quantum chromodynamics, that's computationally extraordinarily challenging even to calculate something like the structure of a proton or a simple nucleus. So using it to calculate something like, you know, a nucleus-sized star, like a neutron star, is incredibly, incredibly difficult. So we can't calculate it from first principles. What we have to do instead is make phenomenological models, or my particle physics colleagues do, and then we're going to go and test those essentially with experiment and with observation. If you're working at a heavy ion collision experiment, basically like the big experiments, for example, at CERN, you're working up towards this top region up here. So kind of high temperature, low to mid densities, basically smacking heavy ions together to explore this. Neutron stars, by contrast, occupy this region, basically down here, again, looking at what happens as you go to perhaps these exotic states, essentially, that I mentioned before. And these are really truly unique within neutron stars. You can't make them in collider experiments because they're essentially the low temperature, ultra high density regime. Several times nuclear density, way more neutron rich than you can ever make in the lab, and the potential for stable states of strange matter. And what you'd make in a collider experiment basically is matter with no net strange that just flickers in and out of existence extremely, extremely fast. So essentially we sit in this context together with people working in collider experiments, trying to understand the overall nature of matter. So that's our kind of motivation, but we're also neutron star astronomers. So I have to find something that I can go and measure with a telescope that's going to actually let me get back to all of this wonderful nuclear physics potentially. And so the loop of logic that we follow runs something like this. We have basically unknown states of matter within the neutron star core. We may have neutron-rich material, we may have hyperons, which have strange quarks in, we may have deconfined quark matter. Now, the composition, the types of particles that are there, and also how the forces between those different particles behave at very, very high density, that's the kind of microphysical uncertainty. But that sets on the larger scale what we call the equation of state. And that is essentially the relationship between pressure and density within the star. In principle, I should talk about temperature in there as well, but the beautiful thing about old neutron stars is you don't have to worry about temperature. If you're doing neutron star mergers or supernovae, I'm afraid you will have to. But fortunately for what I'm doing, I don't have to worry about it. What I'm showing in the top left are various different equation of state models, this pressure density relationship for various different types of composition and calculational methods. So there's a bit of a range of uncertainty there as well. Then, fortunately, I can make use of the stellar structure equations. And we're using the relativistic stellar structure equations because these are strong gravity compact objects, highly dense. But basically, equation of state is one of the ingredients that goes in there. And then I'm just balancing forces, basically pressure gradients and gravity, in order to build a star. Starting from a central density, integrating out, basically, and ending up at the border, changing the central density, basically, and repeating until I build up a mass radius relationship. Basically, and again, these are families of models that occupy some range of space, and it gives you an idea of the kind of uncertainty that we have essentially at the moment with the theories. You know, we don't know for a given mass radius relationship to within a few kilometers what the right function actually is there. Okay, so now I've got to some, you know, property of the star, but these are still really tiny stars, really, really far away. So how on earth am I going to go away and measure perhaps the mass and the radius, the size of these things? And here now I can take advantage of relativity because these are relativistic compact stars. So basically, if I take the mass and the radius, that sets the gravitational field. I add in the spin because these can be extremely rapidly spinning objects. And essentially, I have a prediction for the exterior space-time of the object, the distorted space-time. And again, calculating space-times of rapidly spinning neutron stars is something that we know really, really well how to do. Now, what this means, any radiation coming from the surface of the star has to fight its way towards us through this distorted space-time. And in doing so, it's going to pick up signatures of the mass and the radius. So if I can find the right observable affected by relativity, I can in principle get the mass and radius. I can in principle get the equation of state. Then I can walk down the corridor, hand over an envelope to my nuclear physics colleagues and say, tell me what it means. What's it made of and what is the microphysics? So that is the logic essentially that we're trying to follow. So this is what NICER is trying to do. So let me now introduce you to NICER. This is NICER prior to launch, basically early 2017. NICER is an instrument designed explicitly to use this kind of radiation technique to get at the surface. This gives you some idea essentially of the size of the instrument. It's like a kind of oversized dishwasher or fridge, essentially. It's X-ray concentrator optics. There are 56 silicon drift detectors in there, of which 51 kind of work at the moment. And it's a soft X-ray band telescope. So 0.2 to about 12 keV, comparable, if you know previous telescopes, to XMM Newton, but much, much larger. Twice the area of XMM Newton, has amazing time tagging of photons, far better than the Rossi X-ray timing explorer. So it's designed to get very good spectral resolution and very, very good time tagging of photons. This is one of my absolute favorite photographs of NICER, because I have kids of exactly the right age to be obsessed with Lego and Ninjago. And when they saw this photograph for the first time, they were convinced that I actually was working with ninjas. Very disappointed to discover this is not the case, but very briefly, I was extremely cool at home until they realized that I'm not in this picture and they're not actually ninjas, but never mind. So NICER launched in 2017, went up on a Falcon 9 as part of Crew Resupply Mission 11. And it was installed on the ISS, and there are some great videos that you can download of watching NICER being unpacked, basically out of Dragon and pulled out and installed. So if you've got a spare moment with a coffee, you should go and take a look at those on the NASA website. And this is one of the beautiful things, essentially, about having a telescope on the space station. You can actually go and take pictures of it. You don't just launch it off and say goodbye and never see it again. You can actually go and take movies of it. So this is NICER on the space station. Wildly sped up, but you can see it moving around. So these are the detectors basically here. It gives you also an idea of the kind of complex environment that we're working in. We're obviously tied to the space station. Nice, because we get their data and power arrays and all the rest, but we have to go where they go. And that sometimes restricts the field of view a little bit. We have solar panels flying around in the background. There are other experiments out there. There are transports coming in and out. Sometimes there are spacewalks. So every now and again, you get a fun thing where there's an astrophysical transient we'd love to go and observe. And this happened relatively recently, and there was actually a spacewalk in progress. And so NICER had to be stowed. And my kind of Twitter timeline was half, really annoyed X-ray astronomers who wanted to do something, and people really enthusiastic about the spacewalk, and others just wishing the astronauts would get inside so we could do some astronomy. So it's kind of an interesting environment. I should also mention that NICER is actually designed to withstand a kick from an astronaut. In case one of them accidentally flies past and boots it, it should make it okay out the other side. So that is NICER moving around.
And can I ask, how stable is the space station? Is it like vibrating and stuff? And is that something you also have to worry about?
Fortunately, we don't have to worry about it that much, but yeah, there are odd little things like that. The biggest issue, things like kind of debris and outgassing can be a problem. Just kind of messy astronauts coming in and out has been the biggest issue that we've had to contend with. Okay, so let me say a little bit more about the technique that NICER is using. So I mentioned that in principle, we're using radiation from the surface, looking for relativistic effects on that radiation. But in fact, we're also picking a particular class of neutron stars. We are looking at stars that have non-uniform surface emission, so they're X-ray pulsars. And that means, essentially, we can also take advantage of the spin of the star in our modeling as well. And that helps us to exploit some additional relativistic effects. And you can just get an idea of some of the things that we look at in this little movie here. If you have very weak gravity and you have a hot spot that disappears behind the star, the emission would drop to 0 and we wouldn't see anything. If you have strong gravity, basically in light bending, which we do, which is great, you can see in this particular scenario now, we can see both poles of the star and the spot never truly disappears. So this is one of the relativistic effects, essentially, that we take advantage of, is all of the lensing effects that are going on. And then we're modeling that not just for the overall brightness, but for the entire X-ray energy spectrum, essentially, and looking at how that varies over time.
And just to be clear, those are both the same radius star, but different mass, essentially.
Yeah, exactly. I mean, that's a particularly fortuitous geometry that we're looking at. But yeah, basically the spin adds something to us as well as the very strong gravitational field. If we just had the compactness, essentially we would only get the mass to radius ratio, but adding the spin information in there lets us break those two out and get the mass in principle as well as the radius. So the particular class of neutron stars that we're looking at are rotation-powered millisecond X-ray pulsars. So these are emitting in the X-ray. Basically what's happening is they're rapidly spinning stars. They've been spun up through an accretion phase. Basically, so that we think they're relatively low magnetic field pulsars now, spinning 200, 300 times a second. So they're pretty rapid rotators. So this is the kind of cartoon picture that you have a kind of dipole magnetic field of some kind, particles in the magnetosphere being accelerated along the field lines and smacking into the neutron star surface. Those are then heating the surface up to temperatures that radiate in the X-ray. So they're getting extremely, extremely hot. And there's a very thin atmosphere layer, basically above the crust of the star, essentially, that's getting warmed up and they're radiating. And then there's a beam of X-rays coming from that hot spot. And that is why we are seeing it as an X-ray pulsar as the star spins. So this is thermal emission, essentially, that we're dealing with from a small class of bright rotation-powered millisecond X-ray pulsars. Many of the stars that we're looking at are also radio pulsars. And that's actually quite a bonus because it means that sometimes we have independent information on the mass if they happen to be in a binary, perhaps the distance to the star, and perhaps the inclination. So we can get a little bit of extra information if they're radio pulsars as well. So we then put that all together in a technique that's called pulse profile modeling. So what pulse profile modeling is doing is that, as the star spins, it's a very stable rotator, photons come towards us, get picked up by NICER. We know the spin ephemeris of the star. So for every photon that arrives, we can put it into a rotational phase bin. This is when in the spin cycle of the star it arrived. We can also record extremely accurately the energy with NICER. And so what we do over time is we build up this kind of thing, which is a pulse profile that we just drop counts into a box of rotational phase and energy. And we do that essentially over weeks and weeks and weeks to build up loads and loads of photons. And gradually you end up with something like this, essentially showing, number of counts broken out by energy over time, or essentially all put together by rotational phase. So this is a kind of typical pulse profile here. We then have to have a physical model for what is generating that emission. And this is where the relativistic ray tracing comes in. So we build a relativistic ray tracing model with all that physics in there. Parameters in the model will be the mass and radius of the star, but also other things like the distance, the observer inclination, perhaps atmospheric beaming goes in there, the number of hotspots we have, their size, their shape, their temperature, and so on. And those are all parameters in the model as well. And we have essentially a simulation code that can take any combination of those parameters and generate a simulated pulse profile once we've folded it through a model of the instrument. We then have to do large-scale statistical sampling to survey across that whole parameter space. We're doing Bayesian inference, basically, and eventually looking to obtain distributions of all of those different model parameters. And that's a really computationally intensive process. But what falls out at the end of it are, probability distributions for the mass and the radius. That's what we want, essentially, for our nuclear physics. But also, we get the geometric parameters of the star for free. Of where the hotspots are, for example, on the surface. And if you think about it, these are tiny little stars, size of Amsterdam, kind of mini little things, thousands of light years away. And we're using relativity and X-ray telescopes to make a map of the surface. And this is something that this is a byproduct of what we do. And I think this is the coolest thing, honestly, that we're actually doing with this technique as well. So that's the loop that we run through for the analysis. So this is what NICER was set up and designed to do to get the high quality data to enable this. So now let me show you some real data. We finished analysis now for 2 neutron stars. So here is the pulse profile data for the first 2 stars that we analyzed. What I'm showing on top is the bolometric pulse profile. So this is just the total number of counts over 2 rotational phase cycles. What I'm showing on the left is the first star that we did. It's one of the brightest that we have. So you have up to 30,000 counts basically per bin up here. So it's extremely, extremely intense. This is the pulse profile broken out now into energy channel as well. So you can see this kind of beautiful spectral resolution coming in there as well. On the right-hand side, you'll see a much weaker source, which was the second one that we did for reasons that I'm going to come back to because it's particularly intriguing. So rather than keep on going with the bright ones, we chose to focus our attention on this very weak one. You can see far fewer counts overall. You can see the effect in the pulse profile. The data quality is much lower, but this gives you an idea of the range of things that we're trying. The one on the left is a 205 Hz pulsar. The one on the right is 346 Hz. And this is about 2 megaseconds of data that goes into putting this together. Okay, so several weeks of data taken over the course of a year or two. With NICER, they're super stable. We can just come back to them, pick up more data, go do something else, come back and pick up more data. So very long time to get these data sets. So once we've got our fantastic data, we then have our simulation codes for the relativistic ray tracing, and we have our inference codes, which are doing the statistical sampling and the Bayesian inference. We have a number of groups within the NICER collaboration that had different ray tracing codes. So we spend a lot of time when we set up cross-testing those codes to make sure that we had all the relativistic ray tracing right. Then we moved on to test our inference codes, and this is where things get more computationally intensive. So right now we have 2 main working groups doing inference. My team in Amsterdam using the XPSI code, and Cole Miller's team out of Illinois, Maryland, using an independent sampler and an independent ray tracing code. And the 2 teams work independently on the same data sets to make sure that we're robust to slight changes in samplers, in model assumptions, and so on. Other things that we have to put in there. For example, we have to worry about the telescope. And this is something that when I started out as a more theory-oriented person, I didn't really care about the instrument terribly much. And it would never have occurred to me to worry about the instrument being uncertain in any way, which is another thing. But when you actually start to come into this, the instrument, horrifyingly, is not completely perfect. So there is some uncertainty in the instrument response. And actually, that's one of the things that we also tried to include in our model as well. And so it's the first time in my life I have to worry about calibration uncertainty. I know a lot more words than I used to a couple of years ago. But this is something, the uncertainty and the effective area of the instrument is something that we try to take into account as well in our modeling. Then we come on to the really, I think, the trickiest bit of the modeling that we do. One of the ingredients that has to go in there, as I mentioned, is the number of spots, their shape, their temperature distribution, and so on. So, you walk along the corridor to your colleague who works on pulsars, X-ray pulsars, radio pulsars, and you say, hey, tell me what the temperature distribution is on the surface of a pulsar. And they kind of laugh hysterically and just say, we don't know. It's so hard to compute from first principles what is going on in the pulsar magnetosphere, what the return currents are, what the temperature distribution, the heat distribution is. This is really complicated. And so they give you pictures like this, of possible return current distributions, which you're kind of mapping to temperature in some way. So something maybe like this. It could be a circle, it could be a crescent, it could be a ring. It's like, okay, how are we going to deal with that within our modeling? So one of the things that we also set up, essentially, are parameterized models of various different surface patterns. And we work through models of increasing complexity to see essentially what is needed in order to explain the data. And so we build these parameterized models to allow the possibility of rings and crescents and circles and multi-temperature components as far as we can get them. And we see if we end up with something eventually that looks like the data. So this just gives you some flavor of some of the different models that we're taking. For the data sets that we've analyzed so far, my group have stuck to having 2 separate emitting regions, but they don't have to be opposite each other. They don't have to have the same properties. And indeed, they can have some quite complicated structures as well. So this is something where we now have a lot of interaction, in particular with the pulsar theorists as well. So I should come and show you some results. I say we started with this very, very bright star, not in the binary. So we didn't have an independent constraint on the mass. Our very brightest source, actually, we do have an independent constraint on the mass. And it might have been nice to start with that one, but annoyingly for that one, there is a bright active galactic nucleus in the field of view. So we have to look at it off axis, which meant the instrument response model was more difficult to get a handle on. So in fact, we started with our second brightest source, and that's PSR J0030. And And basically, we ran through this sequence of models, trying out different surface geometries, essentially to see, were there still problems with the data? Were we explaining the data? Did we need more complexity? And working through a series of measures of model quality to try and work out what was the preferred configuration that emerged from this. We end up essentially with an extraordinarily large number of corner plots of posterior distributions of all of the different model variables. So, your eyes kind of end up dislocating at some point, staring at these things for all of the various model parameters that we're dealing with. But out of it, we managed to get the mass and the radius of the star. We do model quality checks, checking the data against the best prediction of the model, looking at the residuals to see whether we're really explaining what we're looking at. And we have lots of other model checks that we do as well. I said it took us a long time, essentially, to come through the model. We didn't get our first results out till the end of 2019, after 2 years of operation. And that was really working through all of these details in the analysis process and trying to understand the various elements. So this is what the map of the surface emission looks like for this particular source. We are looking at it from the Northern Hemisphere, we think. And the two hot emitting regions are actually in the Southern Hemisphere. And if you're Australian, you're quite welcome to flip those things around, basically of Southern to Northern. But basically, we're looking at it from the other hemisphere and the spots are in the far one. One small spot and one very, very long extended crescent, basically, which we see kind of coming across here. So that was the geometry that we came up with. So that immediately takes you back to this lovely picture that I showed you of the perfect cartoon of the perfect X-ray pulsar with the perfect dipole magnetic field.
Can I ask a question?
Yes, of course.
Oh, someone muted me. Yeah, so how conclusive is it in the crescent? Could it be like a large spot of which you're just seeing a ring because it's on the other side, or would that be physically like ruled out?
Yeah, it can't be a ring. We allowed the possibility of ring, and this was a much more strongly preferred model. So it's not a ring. It certainly could be a more long extended oval. So the other analysis team doesn't have the possibility of crescents, but they can do kind of very thin ovals. And their best fit model is very, very similar, but with, if you like, a long thin oval rather than a long thin crescent. So there is a bit of wiggle room in the kind of shapes that you can allow, but I don't think it can be a ring.
I mean, I guess what I was thinking of, okay, is that it's not like that it actually is a spot like a circle, but you're just seeing one crescent of it.
Well, no, because it's spinning around, because of the lensing, we would still get emission, I think, from the rest of the circle on the other, from the rest of the ring on the other side.
Oh, so okay.
So yeah, I think now there are other constraints. I'll come back to some of this at the end, because there are other things we're now going to try and look at. And I think in principle, the model quality wasn't terrible for rings. I should say that. So eventually, if the pulsar astronomers at some point came back to us and said, you can't have a crescent, sorry, we can't make them anymore. I wouldn't die in a ditch about it, because I think we've still got a model that works quite well for that, basically. But for now, if crescents are allowed, this is the preferred configuration.
Thanks.
But for every single model that we looked at, the one common feature was two spots in the same hemisphere and looking at it from the other one. So basically we stick a nice, there's no way you can do that with the dipole. So your standard pulsar cartoon goes in the bin, which is annoying, because lots of us have this 50 years of pulsars conference mug with beautiful dipole on. It's a lie. The magnetic field probably looks something more like this kind of mess, which is a quadradipole type configuration. So a quadrupole component as well as a dipole. So this is kind of fun. The surface map shows the field is a mess. So over to the pulsar theorists and the people worrying about magnetic fields in stars, you need to fix this. Fun consequences for pulsar emission, because this source is also a radio and a gamma ray pulsar. It's like, okay, can we also explain, if this is the configuration, can you still explain the radio emission and the gamma ray emission? Because most of the modeling that's been done has assumed a dipole. So we were pretty relieved to see a paper from Alexander Chen and his collaborators at the end of 2020 saying it's okay, you can still, even with this weird magnetic field, you can still potentially explain the multi-wavelength emission from this source. So that's kind of, again, a nice thing that we can start to fold in there as well. In terms of the mass and radius, let me put our kind of confidence regions, credible regions in context, basically with a few different mass radius relationships from different models. Basically, what you're seeing here is the 68% and 95% uncertainty regions and a bunch of the different plausible models that we have at the moment. And it's 10% errors pretty much across the board. And it's really right in the middle of absolutely everything. So on its own, this measurement didn't terribly cut out any equations of state, but it was a proof of principle, essentially, that we could use the technique to do this. So that's where we sat basically at the end of 2019 with our first results out.
And is it worth following the source up anymore, or is it basically...
Oh, we've got a huge load more data on this source already. So we're actually doing a revised analysis at the moment with a much bigger data set.
And how much better do you think these confidence, these contours would get? With the new,
we should be looking at least a route to improvement because we have about double the amount of data now.
Okay.
So that will be really nice. So yeah, basically, again, the beautiful thing about these stars, they're always there. So you can just, when the sun and the space station allow, you can just go back and point at them and pick up more data. So yeah, JW30, firmly in the middle of the range, nothing extreme. It's like, okay, there we are. And the radius, the mass came out about 1.4 solar masses, which is like the canonical neutron star mass. So it's like, okay, we're done. Boring mass, fairly boring radius. And then our original plan, so I should also mention the independent analysis of the other team came up with very comparable numbers and geometries here as well. We had then planned to go to our brightest source, which has an independent mass estimate with about 3% uncertainty on it. So we were hoping for a very tight radius measurement for that one. But as with all good plans, our radio colleagues surprised us again around 2019 by announcing the discovery of a 2.1 solar mass pulsar. And that's heavy. And heavy is brilliant because it means high central density. And that means all kinds of fun nuclear physics. So our nuclear physics colleagues were already going crazy just knowing the mass of this star. It's faint for NICER, but it does emit in the X-ray. So we made a decision, because it's high mass, and that's really potentially quite constraining, that we would instead focus our observing time and our analysis time on trying to get a radius measurement for this one. So basically, we were lucky enough to be able to work with our radio colleagues. So we got new measurements, basically from GBT and from the CHIME PULSAR collaboration. So basically, they managed to revise the mass measurement slightly and give us measurements of the distance, basically, and the inclination as well, which is great. In addition to NICER, we also happen to have some XMM data for this one. Now, XMM is it's smaller, it's a tiny data set. But the reason why it's nice is that for XMM, it's way easier to get essentially some estimate of the background emission because essentially it's in a much lower radiation environment than the space station. So if you want to get some idea of what photons you're absorbing that are not coming from the star, XMM is really nice. And it turns out this was a really useful little data set for us to put into the analysis as well. So we went ahead and we put together this combined analysis with the new radio measurements as priors on our analysis, the beautiful NICER data set, and also this little data set from XMM that gave us a much better idea of the split between what's coming from the star and what's coming from the other space things that are around, which basically contaminate our analysis, because that's really hard to estimate for NICER at the moment. Starting with the surface map. So here on the left is the one that you've already seen, and on the right is the surface map for this new very high mass star. So this one we're looking at almost edge on along the equator, and that's why we're actually able to get a mass measurement from radio because of it, for Shapiro delay. This time we were okay with circular spots. And again, one's quite close to the equator, one's essentially in one hemisphere, but again, they're both in the same hemisphere again, and they're certainly not directly opposite each other. So once again, the dipole model not working, basically. So that one is also gone. So indeed, it implies, in principle, a more complex magnetic field. So that was the surface map. Coming on to the mass and radius. So again, now we had multiple data sets essentially to play with. So what I'm showing on this slightly complicated plot are, again, our corner plots, 2D and 1D posterior distributions on parameters. For the radius of the star, the mass of the star, and the compactness. And I just want to show you one kind of cute thing in here, or two things, in fact. First is the mass. The mass, we've got the prior distribution in here and the posterior. This is all determined from the radio observation. So basically, without this number from the radio people, we would not have been able to do this analysis. because the NICER data set on its own is a lot fainter and not high enough quality to do it on its own. So having that radio data was crucial. Coming on to the radius, I'm going to start first of all by looking at the compactness of the star. So the blue line is the posterior distribution for NICER on its own. And we got a beautiful distribution of, here's the radius, here's the compactness rather, and here's the associated radius. When we put in the XMM data, everything moves to this red curve here. And so what XMM does is it cuts out high compactness solutions. And what it's doing is it's telling you what's happening with the bit that sits below this pulse profile here. If you can read the baseline here, this is 9,400 counts. So on top of the pulse, there's a pulse bit sitting on top of a massive unpulsed portion underneath it. Some of that unpulsed emission is genuine background junk, right? Other objects in the field of view, particles, stuff we don't care about. But you can also make an unpulsed component if you have a really compact star through gravitational lensing. And without knowing what the balance is between those two, the inference code on its own will allow the possibility of these very compact stars that are extremely gravitationally lensed. And what XMM told us with this little extra data set was, you're lying to yourselves actually, because in fact, this is what's got to come from the background. You cannot have this much coming from the star through these extreme gravitational lensing solutions. And so it cut out the high compactness solutions and shifted essentially the whole radius of the star. Basically, so it moved everything up by about 1 kilometer just by having this background information. So that was a really nice impact of having XMM. Putting that now essentially on the mass radius diagram, here again, 68%, 95% credible regions for the new star up here as well. So again, we've got about 10% uncertainty, even though we had the mass estimate, basically from our radio colleagues, and that's just because the data set is not as high quality as for 0030. What you can also see is there's not a lot of change between the two. As you go up in mass, the radius doesn't shift by a very great deal. So that is already interesting and starts to tell you things about what might be going on with the nuclear physics. But it's really middle of the road. And what you can also see is that these very, very low radius models, what we call very soft equations of state, are starting to be quite strongly disfavored by both of these measurements. So again, that starts to cut into some of the potential parameter space, what might be going on with quarks and so on. So, we're starting now to make some inroads into potential theory, which is kind of cool. Now, this time, the independent analysis that was done came up with essentially a slightly broader distribution for the radius. And that's in part because the priors on their analysis were different. So if anyone wants to ask me about that later, I can go into some of the reasons for the differences. But we both had a consistent finding that these soft equations of state essentially are getting ruled out by these two different measurements. And there's not a lot of change between the two stars. Now, it's nice to plot things on a mass radius diagram. You can already start to squint at theories and say, oh, this one doesn't look like it works, which is fine. But of course, what we really want to do is now a full second phase of analysis to figure out what the dense matter is. And if you remember back to my original plot, we're now doing the step of taking mass radius measurements and stepping back to the equation of state. So now essentially one thing we have to do is come up with equation of state models. And we run through a full second stage of Bayesian inference using those equation of state models and coming up now with parameter distributions for the equation of state models. When we do this, we don't just have nicer results. I mean, it's great that we've got nicer results, but there are also results now coming from gravitational waves, from neutron star mergers, tidal deformabilities, and so on. And also we can then start to fold in that kind of information as well to our analysis. So when we go to the equation of state analysis, typically we'll put in NICER and we'll also then put in gravitational wave analysis. And there are a huge number of groups that have been doing this. I'm going to just present results that are coming from my group in the NICER collaboration, but again, lots and lots of other papers out there as well. One of the things that, of course, you have to do is you've got to make a choice of equation of state model. Most nuclear theorists probably have their own favorite one that they want to work on. What we've done within our group is typically focus on parameterized models that capture multiple possible different equations of state and microphysics in there. One example, perhaps is to express the pressure density relationship as a sum of piecewise polytropes. This is an extremely well-established model that's been used in the gravitational wave community, developed first by Jocelyn Reed and used over a long period of time. So that's one of the models that we use. We constrain things at low density from lab experiments and from chiral effective field theory, basically coming in there as well. So we have some constraints at low density. There are alternative ways of parameterizing this, for example, writing things in terms of the speed of sound. That has also some advantages. But basically, we've taken a couple of different parameterized models because we also wanted to see, were we influenced by our model choices at all? And that is something that right now we are still quite influenced by. But basically, we pick a form of pressure versus density. We have a number of model parameters that go in there. And again, we run through a second stage of Bayesian inference using our mass radius and tidal deformability information. So let me show you essentially how we are doing right now. I'm going to pick one of the models. Basically, let's start with just this one on the left, which is piecewise polotropes. I'm going to continue to show you things in mass radius space. So basically, I'm now taking my individual measurements, if you like, of mass radius, and I'm using an equation of state model to write that now into a mass radius function instead, running through the second inference stage. So in principle, the full prior space that this model occupies is outlined by this black region here. Okay, but actually, if I were to show you the probability distributions within that, it wouldn't be uniform in mass radius space. And that is just purely a function of the way that we specify the model and the priors and the parameters. Okay, we can try and be as open-minded as possible, but just because maths and equations, you end up with some distributions in there. It's important to be aware of what those are before you even start your process, because you need to know when the data are taking over and telling you what you're looking at. So if you go ahead and you first of all say, right, I know that I have a 2.1 solar mass pulsar. That alone cuts down your prior space a lot to the green regions shown here. Basically, this again is 68% and 95% credible regions, just given the existence of a 2.1 solar mass pulsar. So that is where we kind of started off, essentially before we did our latest phase of analysis. So now we can start off by adding in gradually these kind of multi-messenger constraints and the two nicer results that we have. So basically, for example, if we put in the binary neutron star merger, tidal deformabilities, it moves everything a little bit essentially towards the left, the red outlines that I'm showing here. So it shifts you down a little bit. We then add in the nicer measurements, and in particular, the latest radius measurement that we have, and it pushes you back up to the green region. And over here is the equivalent for the other equation state model. So you can see that things are kind of narrowing. They're moving a little bit in time, but we're still, I think, at the stage where we're really dominated by the priors on our equation of state models. So it's a little bit early to say that we've got this pinned down, and we're going to need more measurements from both NICER and gravitational waves to do this. But this is the idea that basically with multiple measurements over time, we'll hone in towards one mass radius function, and we'll finally be at the point where the data are really determining what we see. And then you can play other kind of fun games and say, all right, if I have the equation of states, now I know the maximum mass of neutron stars. And that's rather nice. It falls out of your analysis as well. And then I know when black holes form. And then you can answer a whole bunch of additional fun stellar evolution questions as well. So that's the second phase of the analysis, essentially, that we're all now starting to move into. So what comes next for NICER? Well, we've got senior review coming up. So that's the kind of next fun thing where we hope that the senior review panel like the papers we've written already. We've got 4 new sources coming, basically, for which we're taking measurements, building up really good data sets already, and the analysis has already started. We have masses for a couple of them, basically, which is really, really nice. The next one we are hoping to release has a mass, is the one, it's our brightest source. We've got a great mass measurement from radio. It should lie somewhere on this green band here. And the credible region should be comparable in size in the radius. So this is the kind of next thing. It's a tricky analysis. It's such a fabulous data set that we've got a lot of things still to get right about it. But that's the next one we're hoping to release. We're taking more data on the stars we've already measured. So basically these credible regions will start to get smaller, essentially as the data sets get larger as well. So this will improve, plus new sources will come in there. We're improving our understanding of the instruments, of how to deal with background modeling. We're talking with pulsar theorists about the range of shapes that we allow and how feasible those are. So basically, what we've done so far is a beginning. It's absolutely certainly not an end. Plus, we are starting to get ready for the next generation of missions. Now that we know pulse profile modeling can work and it can deliver masses and radii, we want to do this for more neutron stars. And in particular, we would really like to do this for ones that spin faster. So not a kind of measly 300 hertz, but 600 hertz, the real rapid rotators, because then the special relativistic effects get stronger. And in principle, we can do better in getting the radius. So now we're into territory of accreting neutron stars. They're different source types. We have accreting pulsars. We also have stars essentially where the surface is exploding, and we have hotspots developing. And Tony and I have both worked on these hotspots that develop on accreting neutron stars and bursting neutron stars. We still haven't worked out what's causing it. So there's some kind of fun discussions to have about surface patterns there. So Tony, if you can fix this in the next 2 years, that will be magic. So basically, we've got some analysis challenges there. The spots are not stable. They move around. So we have to figure out how to handle that. And we need new types of telescopes to analyze these as well. We need hard X-ray telescopes. We need multiple square meter telescopes. And there are a couple of possible concepts basically going through study phases at the moment, essentially, that would let us do this. So we're now laying the groundwork essentially for those missions. So I will start now just to wrap things up. Basically, NICER is pioneering a completely new technique, which is pulse profile modeling, to get masses and radii of neutron stars. It has been a lot harder than I think any of us would have thought when the thing launched, to get the different aspects of the analysis pipeline right. We're still learning and making our analysis pipeline better. And that, that's been fun to see how that's developed the last few years. But we've now measured the size of 2 neutron stars, including the highest mass neutron star that we know. Okay, which I think is quite an achievement. And I think the thing that excites me the most out of all of this is just we're making maps of these teeny tiny stars, thousands of light years from Earth, using only photons and a teeny washing machine sized telescope flying around, and some computer modeling. And we're able to do that. And the most wonderful thing about that is we've taken this beautiful NASA mission patch, which you'll notice has this beautiful dipolar, utterly inaccurate pulsar on it, and we've broken it. And that will stay as my best career achievement forever, I think. And I'm still really hopeful that at some point NASA makes a new badge for us. So I'll stop there and take any questions.
Thank you, Anna. That was a really great summary of NICER. Does anybody have any questions? Either you can unmute yourself or raise your hand and I'll unmute you as well. But go ahead, Erica.
Hi, Anna. Very cool
Hi.
talk. It's really amazing to hear what NICER is doing and how it's able to do it. I did have a question just to kind of clarify about the XMM Newton. So those observations are more, you said it's more of an X-ray upper limit on the background. So does that mean that if that upper limit on the background is pushed lower, would that push the EOS stiffer? Is that right?
So in terms of the impact on the EOS, it's really hard because it depends on the geometry of where the spots are. Because we were trying to work out what this meant for the other stars. We have, could we say concretely that it's always going to push the radius up? And the problem is we can't, because it's really dependent on the geometry. So but yeah, the real challenge, I mean, ideally, we wouldn't have to rely on XMM. So ideally, we'd have a nicer background estimate, basically on its own. And the team are working on this. So we do have nicer background estimates, but the worry is they're not completely comprehensive. And they also don't always capture other sources in the field of view. Whereas, for XMM, to some degree, we have a much better handle on that. Basically, and again, it just does not have the high particle background environment that you have on the space station.
Okay, all right, thank you.
So yeah, it was, really just separating out of the unpulsed component that we measure, how much of that is genuine background and how much is coming from lensing of some kind, basically due to spot configuration. I said in a dream world, we'd have a perfect NICER background estimate. We wouldn't have to worry about XMM at all, because it is this tiny little data set that you're then folding into this fantastic quality stuff from NICER. And it pains me a little bit to take the small data set, but it did its job this time.
Okay, thank you.
Go ahead with your question, Anna.
Hi, thank you for the talk. Learned so much. And so, yeah, maybe this is naive, but is there any theoretical kind of room for there to be multiple mass radius relations?
Yes, yes, there are. So there are some possibilities of kind of families of twin stars. Yeah, where you have, one branch basically being separated by some kind of phase transition. And so there've actually been quite a few papers by various different groups looking at what do the new NICER results mean for the possibility of twin stars. Some saying, oh, it may, it's ruling some things out, but not others. I think right now, our results are just not high quality enough yet in order to be able to say anything definitively. But yeah, in principle, there can be two branches. You'd have to have one branch going fairly straight up towards high masses with higher radii, and the potential for one kind of lower radius branch existing with lower maximum mass. But it's certainly possible.
And so with the 4 new sources coming in, do you think it'll be like 6 total, so not that many,
so
but
the two with the tight mass constraints, I think, are the ones that are going to be really interesting. So we've got A437, which is 1.44 solar mass, totally vanilla, middle of the road neutron star down the bottom, but with a very, very tight pre-existing mass constraint. So we're hoping to get a very tight radius constraint from that as well. Then we have one at 1.9 solar mass. Again, much, much higher up, well-constrained mass. So yeah, it will be super intriguing to see whether there's any kind of offset there. Because again, it's bright, both sources are brighter. We should expect to do better than we did for 0740. And yeah, if they do start to be separated, that would be interesting. I think my first thought would probably be there's something going on with the temperature distributions. And I'd want to verify that we couldn't mimic that with some weird temperature distribution. But yeah, looking for an offset would be really interesting, and it's possible.
So exciting. Thank you.
Go ahead, Francois.
Hi, thank you for a wonderful talk. I have a question concerning a comment you made towards the end of this beautiful long story that the spots may be moving around. And my question is that inferred from variations in the pulse period from the X-rays, or how can you distinguish whether the spots are moving around or whether the entire neutron star is slightly speeding up or slowing down due to accretion or something like that?
Yeah, so the changes are sufficiently fast, basically, that there's no way it can be due to something intrinsic in the star. So as an example, the hot spots that form during thermonuclear bursts on accreting neutron stars, you see them shift on second timescales by multiple cycles potentially. Or certainly fractions of a cycle. And that's simply too fast for it to be something intrinsic to the neutron star spinning up and down. Similarly, for the accretion hotspots on accreting pulsars, again, you can track the phase variation, and they're moving around by maybe 0.1, 0.2 cycles on the surface, but over timescales of days. But that's still, if you look at the moment of inertia of a neutron star, that's really fast. It could not be the whole star spinning up and down.
Okay, thank you very much.
So one way to picture it, Francois, almost like cyclones drifting across,
Okay.
rather than the entire star.
I mean, we're very lucky that for NICER, they're incredibly stable. So we've tried, for example, splitting our data set in two, beginning and end and repeating the analysis, and we get completely consistent results. So for NICER, thankfully, we don't have to worry about this, but we really will when we get towards the accreting stars.
Okay. Guillermo?
Hi. Thank you very much, Anna. That was really a beautiful talk. I'm sure you're going to do great on your senior review, I have no doubt. Are there kind of any kind of like unicorn good configurations of something like eclipsing neutron star binaries or transiting neutron star binaries that can give you like a perfect measurement because you basically constrain the geometry or the size independently in some way? And do those systems exist? Are there searches for those?
Yes, so we have, for example, one accretion powered pulsar that has a Shapiro delay measurements. So again, the inclination is such that you're able to get Shapiro delay. Eclipsing systems.
I don't know if everyone knows exactly what that means. Could you just describe that?
Yeah, sure. So basically what we're seeing essentially is radiation, because we're looking at it equatorially. Basically, we're seeing essentially changes as the radiation from the other star propagates through essentially the potential well, basically, of the two stars as they orbit around each other. And so basically, if you're super lucky enough to be seeing exactly edge on, then as one star gets behind the other, the radiation has to propagate through the potential well of the other. And so it gives you an independent relativistic constraint, essentially. And so you can therefore, via that, pick up potentially a really good measurement of the mass of the system. And that's what we did for 0740, basically, which is in a binary, essentially with a white dwarf as well. But we have an accreting system, again, perfect, eclipsing. So the inclination is really strongly constrained because we know it's eclipsing. So potentially, yes. Annoyingly, a lot of the burst oscillation sources, which are very bright, very fast, don't do this, which is irritating. It would be nice if we could find one. I guess the one lovely thing is they're transient, and new sources do appear from time to time. So yeah, we're keeping an eye out for them, with the hope that at some point a fortuitously fantastic source, 700 hertz rotation, eclipsing with burst oscillations will be the absolute dream, basically, to be working with.
Thanks.
Elva?
Yes. Hi, Anna. Thank you
Hi.
so much for this very nice talk. I learned a lot. And I was curious because you show here in the very last slide and also during the analysis that the neutron stars, they have a weird magnetic field configuration. And it reminds me a little bit of how magnetic fields can look like on massive main sequence stars, for example. They're really kind of unoriented chaotic structure. Do you think there is a correlation between that, or how, where do you think this weird structure would come from? Do you have any fun ideas about it?
So I have no idea at all. Either it's from the supernova, so it's coming from the parent star, and then it's got to survive through this whole lifetime, because these are old stars. So they've been through an accretion phase, they've recycled, and the field has to stay weird that whole time. So, if you want to make it a supernova, it has to stay weird. I mean, I talk to supernova people who tell me it's fine to make weird, but then it has to last. Alternatively, I guess the question is, could you make it during the accretion phase? So could you modify the magnetic fields during that phase to build up this kind of weird quadradipole type structure? So that's, I think, another possibility. And one of the things that we're now looking at is, if they were like this during the accretion phase, what might they have looked at? So we've a PhD student called Pushpita Das who's doing some simulations of this at the moment, to say, if you had that kind of crazy structure and it was accreting, would it look like a pulsar or not during the accretion phase? And it might well not do. So that might explain why lots and lots of accreting neutron stars don't appear as pulsars, because the field is too weird to actually allow it. The accretion is just kind of a mess onto the field structure. But yeah, where it comes from, I really don't know. I'd love it if someone could fix it. The other alternative is this, that we have something really wrong in our model. They are perfect dipoles, but some element of the way we're modeling the atmosphere or the sort of surface patterns we're assuming doesn't give us an antipodal configuration. We've just not found any good antipodal configuration that works. So, if anyone has any great ideas for weird things we're missing, that we could also try that out. But yeah, I have no idea where the fill comes from.
I mean,
I have no problems with that. It looks like that. I think I think it's totally fine, but it's really interesting that it's similar. What did you say, Tony?
Oh, well, there's main sequence stars like you were mentioning, but there's also magnetic field mapping for white dwarfs, which also show a lot of higher components. Sometimes they even show like a dipole component, but it's like misplaced. It's not even centered on the star. So, and
I mean, it's kind of funny. I mean, when we kind of put this out, all the pulsar theorists, of course, no one expected it to be a dipole. It's like, but you're all publishing papers with dipoles. So yeah, because we can calculate it. It's like, okay. So I think no one is worried about the idea of doing this. It's just, it's hard to compute, basically.
Great. Well, thank you again for a really nice talk, Anna, and hope you enjoy some of your one-on-one meetings the rest of the day. But yeah, and everyone else have a great day. Thank you.
Thank you.